So if it's okay, I can go forward with those activation functions, and after that, we can go back to the examples.
Okay.
Yeah. So I will share the link with you. So, okay. So the activation function can be divided into two types. In fact, we have some linear activation functions and some nonlinear activation function. And the most important, in fact, is a nonlinear activation function. So this is the most important for us. So linear activation function, it's very similar to the one which we used in adaptive linear unit, linear activation function, which like this one, right? So we used this one for regression problems. Nonlinear activation functions, they are very important because they can add some non-linearity to the neural network layers, for example, and it's important to try to model and map complex relationships. So we can start with the unit step or the hard limb. I mean, this unit step function, some people they call it hard limb function. And there are two types of it. It's a symmetric. We have this hard limb and the symmetric hard limb. So we have hard limb function like this one, which can convert the input from its range into 0 and +1, as you can see here. So this is a function. This is unit step. We call it unit step. Unit step. So in fact, it converts x from its range into a number between 0 and 1. So if you have any x value here from 0, so imagine that you have any positive value for x from 0 to infinity, all those numbers will be converted into +1, right? All those numbers will be converted into +1. On the other side, all negative numbers, all those negative numbers will be converted into 0. Right? So this is a step function. Symmetric, it will convert numbers between -1 and 2, -1, +1, and -1. So it will be like this one, right? So it will be like this one, +1, and also -1. So it's this is the function, right? So the input here will be x, and the output will be f of x. So it will convert all positive numbers into +1, and it will convert all negative numbers into -1. So it has this kind of, they call it squashing impact or something. So it is used for binary classification, and the derivative of this unit step is delta, which is impulse. The first derivative of this function will be impulse function. So we don't use it, in fact, with gradient descent because of this problem, because it's a 0 everywhere unless other and at 0 it's +infinity, as you can see here. So it's like this one. So it's a very, very strange derivative of this function. So we don't use it with gradient descent. Sigmoid function, it is used as a squashing function. This is a sigmoid. This one is a sigmoid function. As you can see, it converts inputs. I mean, from 0 to +infinity, it will be converted into that part, right? So it will convert it into, it will be maximum +1 at some point. And all negative values, it will be converted into that part, right? So it is used as a squashing function, which limits the output into a range between 0 and -1. It limits the output between a value between 0 and +1. So all values will be converted into a number between 0 and +1. So it has this squashing impact. So all x values from 0 to infinity and all negative values from -infinity to 0, all those numbers will be squashed into a number between 0 and 1. So imagine that you have, for example, 2.5, it will be converted into this number. 10, it will be converted into this number. 10 million, it will be converted to a number close to 1, right? So this is the function. It predicts probability of a binary classification problem. It is used for calculating the probability of a binary classification problem. You have two classes, for example. For example, dogs and cats, we can use this sigmoid function for calculating the probability of binary classification problem. The mathematical formula for it, it's like this one, sigmoid. of x, it's 1 divided by 1 plus exponential minus x. You can multiply above and below by exponential x, so it will be exponential x divided by exponential x plus 1. If you want to find the first derivative, so this one we can say that this one we can write it like this one, 1 plus exponential minus x to the power of minus 1. If you want to get the first derivative, so it will be minus 1 multiplied by the function, subtract 1 from this one, so it will be minus 2, multiplied by the first derivative of what is inside. So the first derivative of what is inside. What is inside? It will be 1, it will be 0. Exponential minus x, it will be minus exponential minus x. Minus minus, it will be plus. So it will be exponential minus x divided by 1 plus exponential minus x squared. Try to make it simple, for example, so just add 1 and subtract 1 again. So you have that part, divide that part by that part, so it will be 1 divided by 1 by plus exponential minus x minus 1 divided by 1 plus exponential square. This one, in fact, it's our function, which is sigmoid x. This one, it's sig x, sigmoid of x. This one, it's sigmoid x square. So it will be s minus s square, or it will be sigmoid of s multiplied by 1 minus sigmoid. If you call it f, for example, so I can just call it f equal 1 plus exponential x. So the first derivative of this function, it will be f multiplied by 1 minus f. Correct? So it's very easy, this sigmoid function. And if you want to plot it, it will be this green part. So the red part, it is a function. This is a sigmoid. This is a sigmoid. And the green part, it is the first derivative. So this is f. This is f dash. F dash equal f multiplied by 1 minus f. So this is the sigmoid function. So this is one of the most famous activation functions. Softmax, it's something similar, but it calculates the probability for multi-class classification. This softmax, very, very important in deep learning, softmax layer. So softmax is known as normalized exponential function. It's normalized exponential function, and it calculates the probability distribution of the event over n different events. So it calculates the probabilities of each target class over all possible target classes. So if you have 10 classes, so it will calculate the probability of class 0, for example, divided by the summation of all other classes, plus 1 divided by the rest. So it's normalized exponential functions equal it normalized exponential function. So for example, if you use it for any multi-class classification, for example, dogs, the cats, and the elephant, so we should expect that the output will be exponential x divided by the summation of all exponentials. So it will be, you will calculate that part, which is the probability that this image belongs to class 0, divided by all other probabilities, all probabilities. So we should expect that you will get a number, and the summation of those all numbers will add to 1. So the range will be a number between 0 and 1, and the sum of all other probabilities will sum to 1 as well. If the softmax function used for multi-class classification model, it returns the probability for each class where the target class will have the highest probability. Softmax is multi-variable function. We don't use it for binary classification, but we use it for multi-class classification. So you would not take a softmax of a single variable because we need to divide by the summation of all other probabilities. So we can use it for minimum binary classification probability. We can use it for binary class classification and the multi-class classification. It's just if you want to implement it, this is the softmax, and the equation is it's exponential x divided by summation of exponential x. I mean, if you want to implement it, it will be this one. So if you want to implement it in Python, so it should be exponential x divided by summation of exponential x's. This one will be a vector, right? X here will be a vector for multi-class. If it is two values, for example, a and b, for example, right? So it will calculate the probability of a plus probability of b. So it will be probability of a divided by summation of a plus b plus exponential of b divided by exponential of a plus exponential of b. So we call it softmax. So for example, if you have this vector, for example, 2, 3, 5, and 6. So as you can see, this is the output, right? So it will be exponential 2 divided by exponential 2 plus exponential 3 plus exponential 5 plus exponential 6. So it will be this number. This one, it will be exponential 3 divided by the summation. This one will be exponential 5 divided by the summation. This one will be exponential 6 divided by the summation. If you take the sum, if you added those 4 values together, it should add to 1 because it's a probability, right? Another function also, which is very famous also, it's hyperbolic tangent function, which is called tan hx of x, this function. As you can see, the range of this function is a number between -1 and 1. So it does squashing similar to sigmoid, but sigmoid, it try to perform squashing between 0 and 1, but this one, it will do the squashing between -1 and 1. So we have here from -1 until 1. So it will squash all input values into this range, -1 to 1. And sometimes they call it sigmoidal or S-shaped symmetric function. It's a symmetric. If you can compare it with sigmoid, which is like this one, it's more symmetric. Mathematical formula for it, it's exponential x minus exponential minus x divided by exponential x plus exponential minus x. And if you want to take the first derivative, it will be 1 minus tan h squared. This is the function, and the green one, it's the first derivative, which is a gradient of this function. One function which is very famous, very famous and very important, it's called rectified linear unit. Rectified linear unit. This function is very important. As you can see, this is the blue one. Rectified linear unit. This is the blue one. And as you can see, it converts all negative x values into zeros, and all positive values into the same number, because this one, it's a linear function. That part, for positive x values, it's linear, and the output for negative values, it's a 0. So if you want to, you can say that it's a maximum between 0 and x. So if x is negative, imagine x is -1. So what will be the maximum between 0 and the -1? It will be 0. So now it will convert all negative values into zeros, and it will convert all positive values into the same value. So if x is 5, so what is the maximum between 0 and 5? It's 5. So it will be this line. So it has a range from 0 to infinity. Yeah, it's because it converts all input values into a number between 0 and the plus infinity. Correct? So the range, it's from 0 to infinity. ReLU activation function turns the negative input values into zeros. It will convert all negative values into 0 immediately, which in turn affects the resulting graph by not mapping negative values. Negative values will not be mapped. It will be converted into zeros. So if you have some negative values, those negative values will disappear. All those negative values will be converted into zeros. So if you are working with a data set, and if your data set has some negative values, so if you have some input features which are negative values, those negative values will be converted into zeros. You will lose those values. So when you are selecting the activation function, it's very important to look into your data, because it will not map negative values. And all negative values will be converted into zeros, but all positive values will stay as it is. Soft plus is a smooth approximation to the rectifier. The soft plus, it's like this one, because it will convert. It will be like this one. I will draw it here. So the positive part will be the same, but the negative part will be like this one, which means it will be able to try to map some of those negative values. Soft plus is a smooth approximation to the rectifier. This green one. This green one, it's a smooth approximation to the rectifier. And the first derivative of the ReLU is a step function. The first derivative of this function is step function. And the first derivative of the sigmoid is, the soft plus is a sigmoid. So it will be like this one. So if you are using ReLU, this is a dotted one. The first derivative of this function will be step function, will be this one. If it is soft plus, so the first derivative of the soft plus will be sigmoid, right? So the first derivative of rectified linear unit is step function, and the first derivative of the soft plus is sigmoid, right? So it will be like this one, and this is how can we plot it. So you need to define, if you need to plot it, you need to define values for x, for example, from -10 to 10 with a step of 0.1. ReLU, it will be a maximum of x and 0. Soft plus, it will be log 1 plus exponential x. This is the first derivative. If you want to get the first derivative of ReLU, it will be step function, right? And the first derivative of the soft plus, it will be sigmoid. Why it is important to have a function which is differentiable? We know it's important that this function should be differentiable because we need to calculate the gradient, because we will use gradient descent as an optimizer. If you use gradient descent, so your function must be differentiable. Otherwise, you will not be able to find the formula which will be used for adjusting your weights. Just main use of differentiation is to find the gradient of the function at any point on the graph, right? Because we need to find delta omega. Delta omega, it's minus eta multiplied by partial e by partial omega, which is the derivative. So this function should be differentiable. Otherwise, we will not be able to calculate delta omega. When updating the curve, to know in which direction and how much to change or update the curve depending on the slope. If the slope is negative, so in this case, you will be moving from that side into that side. If it is positive, like this one, so in this case, we will move from right to left. We will move into that direction because we need to reach that point. So this is very logic. So you need to find yourself on the curve. You need to calculate the gradient. If your gradient is negative, in this case, I will move. With the gradient. I will move in the direction which will increase the value of x. If the gradient is positive, so in this case, I will move in the opposite direction, which is the direction which decreases the value of x. The example which we used before, this is our function. We need to calculate the gradient, so I need to find x, which will minimize y, for example. So I need to find the dy by dx, so it will be 2x minus 2. And after that, I will select, if we are here at that point, for example, I will calculate the gradient at that point, which is dy by dx at x equal -1. So it will be -1 multiplied by 2 minus 2. So it will be -4. As you can see, slope is negative. And I need to adjust x, correct? We need to select, we will use this one, right? So we need to select learning rate. So it will be minus eta multiplied by this gradient, which is -4. So it will be -4 multiplied by minus eta. So it will be 4 eta. So now we are moving with a positive value. We have a change rate, or how much change we need to update delta omega. It will be positive value. So in this case, we will move from that direction into that direction. Substitute the value of x, for example, here. So x equal -1, x equal -1 plus delta x, which is 4 eta. If you selected eta equal 0.1, for example, so it will be -1 plus 0.4, so it will be -0.6. So now we will move from -1 to 0.6 here. Next step also, we will move a little bit and so on until we reach that point. And when we are reaching that point, we call it saddle point. The slope at that point should be 0, right? So when the slope is 0, what will happen? Delta x will be 0. So we will stay here at that point. There are lots of activation functions. So this is just examples. So this is, we call it identity matrix or linear transfer function, for example. So f of x equal x, right? This is a step function, which is hard lim. We use this with a perceptron, correct? Binary step function. Logistic, this one, it's a logistic one divided by 1 plus exponential minus x. This is the first derivative. This one is very, very important because we use gradient descent for updating values of weights. This is logistic. This is hyperbolic tangent, correct? Arctan, for example, rectified linear unit. This one called rectified linear unit. This one soft plus. This one, it's called the parametric rectified linear unit. this one exponential linear unit. Those are very, very famous and very important activation functions, which we need to know. And I mean, in this table, you have the function and you have its derivative, and the derivative is very important if we will use gradient descent for adjusting our weights. Very important to look into derivatives of those functions, because the derivative is very important, because this is a gradient. So what is the derivative? In fact, this is the gradient, right? So if we need to get delta omega equal eta minus eta multiplied by this, for example, omega, for example. So this one will be the first derivative, which will be partial f by partial omega. We have here sigmoid functions. This is the derivative of the sigmoid function. Do you see? When this sigmoid increases, it's better, in fact. So I have this figure here because I want to tell you that maybe this step is very good, the step function. This one, it's very, very good because it's a very large, the gradient is very large value, right? Maybe the second best, it could be the soft plus, correct? Which is this function, which is this sigmoid. So first we have step, and after that we have this sigmoid, right? And after that, maybe we will have this hyperbolic tangent. Maybe this is number third, best one. And after that, we will have the blue one, which is the derivative of the sigmoid, correct? And so on. Of course, the Gaussian is not good. We have a Gaussian function, which is this negative, positive. So those derivatives of the activation functions are very, very important because they are connected with something called the vanishing gradient. Vanishing gradient means that the gradient will be very, very small value after some iterations. And then when it is small, this delta omega will be small. And then when this delta omega close to zero, what will happen? We will not be able to adjust our weights. When delta omega close to zero, we will not be able to adjust our weights. So ReLU and the vanishing gradient, this is just a comparison between sigmoid and ReLU. This is my sigmoid function. And this is the first derivative. So the gradient, I will just make it, this is my gradient. Do you see the gradient is very small? If I can compare it with ReLU, because the first derivative of the ReLU will be step function, or if it is soft plus function, which is the blue one, it will be this sigmoid. So I will just try to shade it. Do you see the difference? Which one is larger? Right? So the gradient, when the gradient is larger, it's much better because we will try to have less vanishing gradient impact on our model. So it will be this one. So of course, people today, instead of using a sigmoid function, which has this low gradient, we can just use ReLU, which will have a step gradient, step function, or soft plus, which will have this sigmoid, right? So we can go also to those examples, the links here, and try to see. And if you have any questions, you can ask those questions. So what is vanishing gradient problem? Vanishing gradient is encountered when training artificial neural network with gradient-based learning methods and backpropagation. So because in gradient-based learning methods and backpropagation, we calculate the gradient. And if this gradient is small, what will happen? Delta omega will be close to zero. Because delta omega equal what? Equal minus eta multiplied by the gradient. So if this value is very small, the delta omega also will be very small. And the step size, I mean the value which will be used for adjusting the weights will be very small. So maybe we will not adjust weights at all because omega equal omega plus delta omega. If delta omega is very small, so new omega will equal to old omega. So we will not be able to train our model. So it describes a situation where a deep multi-layer feed-forward neural network for a recurrent neural network, for example, is unable to propagate useful gradient information from the output end of the model back to the layers near to the input. And hence, the inability of the model with many layers to learn on a given data set or to converge to a poor solution. Maybe your model will not be able to learn at all, or maybe it will converge to a poor solution. In gradient-based learning, each of the neural network weights receives an update proportional to the partial derivative of the error. Yeah, we adjust it by a value proportional to that part, because this one is constant. It's negatively, in fact, proportional. So if that part is very small, so what is the value? Delta omega will be small. And when delta omega is small, what will happen? We will not be able to adjust our weights. So we will try to train the model. We will see that it is, I mean, we spend the time for training the model, but the model will not be able to train because the gradient is small. So it is better to use a function with a large gradient like this one, not this one. So in some cases, the gradient will be very small, effectively preventing the weights from changing its value. And in the worst case, this may completely stop the neural network from further training. As one example of the problem cause, traditional activation functions such as hyperbolic tangent function have gradient in the range between 0 and 1, right? And of multiplying n of these small numbers, if we will do some multiplications, if we have multi-layers, and we will do some multiplications, because I need to reach the layers closer to the input. In this case, we will try to multiply those small values several times. So if you are multiplying 0.1 times 0.1, what will be the result? It will be 0.01, so it will be even smaller, right? It will be even smaller. So this means that the error signal will decrease exponentially and we will not be able to adjust our models. When weights of the front layer don't train or don't change, front layers transfers ReLU, transfers random inputs to the preceding layers. For example, if you have a model like a perceptron, you have two inputs, right? We have here x1 and x2 multiplied by omega 1 and omega 2. If we are not able to adjust those omega 1 and omega 2, because we initialize omega 1 with omega 2 with some random values, right? So in fact, what my model will be able to see, it will be a random value multiplied by x1 plus random value multiplied by x2, which is random value. So if you are not able to adjust weights, if you are not to adjust it in the correct direction, which minimize error, your model will see random values all the time. Learning modes, we talk about stochastic gradient descent, batch gradient, and the mini batch gradient. Batch gradient, it's like all the men moving carefully and wisely, because it is very careful. It takes time to calculate its next step, because we need to calculate the gradient over the whole data set. And after that, I will take the average, and after that, we will move. So it's a very, very careful. It's like an old man who spends time thinking, deciding, and he gives enough time for his decisions. It is used to minimize the cost function by taking a step in the opposite direction of the cost gradient from the whole training set. Very computationally expensive, especially for large data sets with millions of data points for the batch gradient, because I need to have a memory which can handle all my data sets. And after that, I need to calculate those batch gradient or whatever. I need to calculate the gradient for each example, and at the end, I will calculate the average or the mean gradient, and I will use this mean gradient for adjusting my weights only one time. So it will take huge time. So in stochastic gradient, as you can see here in this equation, we calculate delta omega. So it will be eta multiplied by error multiplied by x. If you want to use adaptive learning rate, this one, it's adaptive learning rate. So it will be constant divided by number of iterations plus constant, for example. If it is batch gradient, in this case, we need to calculate, it's eta multiplied by this gradient, in fact, negative. So the gradient here, it would be negative error multiplied by x. If you want to calculate it over a batch, so in this case, you need to decide what is the batch size. It could be n values. So you will take the summation of t minus y multiplied by x over n. Right? So it will be the summation. So this is batch, and you need to take the mean of this one. So we need to divide it by n, right? So it would be eta divided by n multiplied by the summation. So it's a mean gradient. So On the other side, so this is batch gradient. On the other side, batch gradient, stochastic gradient. It's iterative or online gradient descent, and it's like a drunk man moving down a hill, almost in instability and powerlessness. So he doesn't care. He's very quick. So instead of updating the weights based on the sum of the accumulated errors over the samples, we update the weights incrementally for each training sample. So we do n updates each epoch. If the size of your data set is n, you will do n updates in each epoch. It reaches conversions much faster because of the more frequent updates. Gradient is based on a single training example, and therefore the error surface is noisier and can escape shallow local minima. To obtain satisfying results using stochastic gradient descent, it is important to shuffle the training set for each epoch to prevent cycles. In stochastic gradient descent, learning rate eta is often replaced by adaptive. This one is adaptive, right? Learning rate that decreases over time. So we're starting with maybe when number of iteration equals 0, so it will be C1 divided by C2. When number of iteration equal 1, so it will be C1 divided by 1 plus C2, and so on. So it starts with a large value at the beginning, and after that it goes down. Can be used for online learning, where our model is trained on the fly. As new training data arrives, in order to learning, the model can immediately adapt to changes, and the training data can be discarded after updating the model if the storage space is an issue. Mini batch gradient, it's a trade-off between both options. So it's like young man actively moving down a hill. So it's understood as applying a batch gradient descent to a smaller subset of training data. For example, if we have 32 samples at a time, the advantage over batch gradient descent is that conversion is reached faster by mini batches because of the more frequent weight updates. It can be used to update the mini batches abroad, for example, or. So now we will have a home assignment. So this home assignment, we have a problem. It's adaptive linear unit, which we used it for classifying MNIST iris datasets, and I used, as you can see, if you can remember last example, it was stochastic gradient descent. So now we need to convert it into batch gradient. And we need to repeat it using stochastic gradient and the mini batch gradient, and we need to do some comparison between our results. So first, I want to show you batch gradient against stochastic gradient. I mean, you can go to the link. That part is okay for initialization. This part is for predict, right? There is no problem at all. But in the training part, this is the tricky part. So if it is batch gradient, we need to do what? If it is batch gradient, we need to calculate the average gradient and use it for adjusting the weights one time each epoch, right? So in this case, what should we do? We need to calculate the gradient, which will be the error multiplied by x. So for each example, we will calculate the error. I mean, we will apply here all data points. We will get an net. I mean, net equal x multiplied by omega plus p, for example. You will send all x values, your batch, correct? You will get net. This one will be a vector. Y equal net, because it's a linear activation function. Calculate error, so it will be t minus y for the whole data set. And after that, you will multiply this error by x and take the mean value. So now this one will be only one value. You will use this one value for adjusting your weights using multiplying it by eta. You do it for omega, you do it for p, calculate the error. If it is a stochastic gradient descent, now in this case, we need to have another for loop, right? I need to do it one by one example. So I need to define another for loop here, where we will go through all my batch data, and then we will use it example by example, calculate net. So it will be dot product of omega multiplied by this x value plus omega 0. And once you have net, you can get y. From this one, you can calculate error. Once you have the error, you will adjust the weights. So as you can see here, it will be error multiplied by input. not error multiplied by input dot mean, but error multiplied by input. This one will be eta multiplied by error directly. So now we can implement batch gradient and stochastic gradient descent. This is how, when you train your model for batch gradient, for example, I don't know if this one, it's batch gradient. As you can see, I trained the model for the same number of box, which is 70. You can see this curve, which is noise curve, and this one it's for batch gradient. This noisy one, it's for stochastic gradient. This noisy one, because I mean, from example to example, it will try to get different numbers. So you will get this strange map, for example. And as you can see here, both models can classify our two classes correctly. Yes, so now we are finishing, but I want you to go to this example. So the home assignment will be plot the decision line or plane in 3D, for example, implement mini batch gradient, make comparisons between batch gradient, mini batch gradient, and stochastic gradient descent, and try to calculate running time. So try to compare between batch gradient, mini batch gradient, and stochastic gradient in terms of running time, how much time we need, right? So running time, for example, running time, oh my God. Running time, memory use, accuracy, computational cost. So we need to have this table, and we need to compare between batch gradient, mini batch gradient, and stochastic gradient descent. So, so I will copy this. We finished now slide number 3. If you have any questions, please ask those questions. I will share this link with you so you can start working with the example, and you can try to present your work maybe after 10-15 minutes, for example, right? So I will share this code with everyone. So try to go to this example and try to modify it. I mean, as you can see here, we have here batch gradient and stochastic gradient descent. Try to implement mini batch gradient and try to make comparison between the 3 modes. Yes. Thank you very much for today. I will stop lecturing now, and the rest of the time we will use it for working with examples.